Last video of the section. Now, don't get overwhelmed. Don't worry about this stuff I wrote down, because again, similar to this last situation where I wanted to show the process, and it wasn't necessarily that I need you to be able to do all of these steps. I want you to get big picture ideas right now. We're in the very first section of the whole class. I want big picture ideas so that we can fit the details into that big picture. So I don't want you to get bogged down in these details. But let's talk about a more complicated model and then see some cool ways of where it comes from and then some problems that we might run into. Okay, so what we're going to talk about now is a predator-prey system. So let's say we have rabbits and foxes. These are going to be our dependent variables. And we're going to have 4 parameters. All right. This is going to be our independent variable, time. So you have rabbits and foxes, and we have a couple premises that I'm not writing down here just because I don't want to go through a whole paragraph. But the idea, right, is that if we have rabbits and foxes, the rabbits are the prey, the foxes are the predators. The more rabbits there are, the more the foxes are going to eat them. Foxes eating the rabbits is going to lead to more foxes, right? Foxes eating rabbits, going to lead to fewer rabbits. Now, if there weren't any foxes, the rabbits would grow exponentially. Of course, if there weren't any rabbits, the foxes would die. They wouldn't have anything to eat. Okay, so a bunch of assumptions here, and then we'll have some parameters that kind of govern this. We'll have a growth rate for the rabbits and a death rate for the foxes. We don't really need a death rate for the rabbits because the rabbits are going to die from the foxes. Similarly, we're not going to really have a growth rate for the foxes because we're going to have the foxes essentially grow based on some constant relating the rabbits and the foxes. And that will have a similar constant for the rabbits, right? The more interactions between these rabbits and foxes, that's more food for the foxes, more deaths for the rabbits. And it turns out you can get something pretty interesting. We're going to get what's called a system of differential equations, and it's going to look like this. So, again, you don't need to know where this comes from. I have a short hand-wavy introduction, but I kind of want to show the process. The rate of change of the rabbits over time is going to be, so if there were no foxes at all, this is what it would be. If there were no foxes at all, right, it would just be the growth rate times the population. We started this whole class with that situation, right? If we had unlimited growth, the rate of change of a population is proportional to the population itself. So if there were no foxes, this would be how the rabbits grow. But because there are foxes, we're going to introduce this beta term, right? The rabbits are dying based on this interaction. So we're going to write it like this. There's some constant, and then the bigger the rabbits and foxes are, the more the rabbits are going to get eaten. And that's why this is a minus term, right? Because this is talking about the rabbits getting eaten. That's going to be a negative rate of change for the rabbits anyway. Because this whole equation is just an equation for the rabbits. But we're also going to need an equation modeling the foxes. So we're going to say the rate of change of the fox population over time is going to be very similar. Now notice this is a little different for the first part, right? Because this is a death rate for the foxes. Death rate is a decline in foxes. It's going to be a negative rate of change. And, oops, a little typo here. So it's proportional to the number of foxes, right? More foxes will die if there are more foxes from starvation. Okay? But there's good news for the foxes. And the good news for the foxes is that that population can grow if there's a lot of rabbit and fox interactions, if the foxes are able to hunt. So we have a somewhat symmetric equation for the foxes. Now we can't solve these individually because, right, the rate of change of the rabbits has to do with the foxes. And the rate of change of the foxes has to do with the rabbits, so they're all intertwined. right? It's an ecosystem. There's a relationship here. And so what we have right here is what's called a first order system, right? You've talked about systems of equations. This is a system of equations too. It's just a system of differential equations. All right. Now these can be more difficult to solve. And in fact, this system right here, we actually can't solve it analytically, as far as I've known and from what I've read and what our textbook claims. We can't solve this analytically. Nobody can. So if you can solve it analytically, I'd love to see it. But we have to use analytic methods like we did in the last thing, or numerical methods using computers to approximate solutions. So yeah, like we can definitely do analysis and say, oh yeah, if there's a bunch of rabbits, the foxes are going to grow. If there's a bunch of foxes, well, the rabbits are definitely going to get eaten. And then there's not going to be enough food for the foxes, so the foxes will also decrease, and then the foxes will decrease. And now the rabbits have a chance to grow, but then the rabbits are going to grow, and then there's going to be more things for the foxes, and you get this very interesting thing that changes over time. Okay? And there's also an equilibrium solution here of 0, 0. If there are no rabbits and no foxes, it's going to stay that way. And then there are also some more interesting equilibrium solutions as well. If you want to look at the equilibrium solutions, well, just set each side equal to 0 and see what you get. All right. So yeah, this is a first order system. We're not going to solve this, but it is a pretty cool predator-prey system. There are more complicated ones as well. You can kind of see where each piece comes from, which is really interesting when you're talking about modeling. It's like, say like, oh yeah, this is the exponential growth piece of the rabbit population. This is the exponential decay piece of the fox population. It's like kind of cool to be able to identify those pieces. It's like, yeah, it's positive because this will lead to the growth of the rabbits. But this part's negative because the foxes are going to lead to the deaths of the rabbits. And yeah, this specific model was used in like World War I to talk about like the number of like sharks in the Mediterranean Sea when there was like a decrease in like predator prey fishing, or in specifically, sorry, the prey fishing, I believe. Yeah, in the fishing of the prey, of course. Yeah, and so that's interesting. And it can also be used to talk about the effects of pesticides in like predator prey insect populations. So I feel like this is, I don't want to say this is intuitive because this probably looks like nonsense, or it probably looks like a headache, but it's relatively simple and can do really, really powerful things. And again, that's the thing about models. Even simpler models can be very powerful for seeing how things go. In my pre-calculus classes, I always like to show a graph of logistic growth models for the spread of COVID. That was like, it's really, really good modeling with just the simple logistic growth models. And of course, there's other models that model it much better, very useful for predictions, for decision making, and all that sorts of things. So it's very exciting. But I'll stop myself there. We're going to end with one final conclusion to the section, is that we have these models. And once we get to the differential equation or system of differential equations, there's kind of three main ways that we can deal with that, right? We can look at analytic solutions, and we did that, right? We did analytic solutions back here. I didn't tell you how we found this solution, but we found an analytic solution. We found a formula of a function that was a solution to the differential equation. Solution meaning it makes the equation true. So sometimes we're going to do that. In fact, pretty soon we'll talk about a method of how we can find analytic solutions for certain equations. We'll also look at analysis, qualitative analysis. And we did that a bit with the logistic growth model. Qualitative analysis was this sort of thing, right? When we talk about, All right, how does P prime changing with relation to P? How can we draw some graphs of what that might look like? We don't need to find the equations of these functions, these solutions, but what might that look like? And we're going to do that a lot again later on in this chapter with something called phase. Oh my gosh, I'm getting all tongue-tied, but slope fields rather. Okay, slope fields are super cool ways of, and pretty simple ways of qualitative analysis. I love that. And then we'll also talk about numerical methods, how we can approximate the solutions with computers. So that's our main foundation going forward. And yeah, it should be a lot of fun. We'll talk with a pretty simple method of Euler's method in this chapter. There's more complicated methods later. But again, it's like so simple, Euler's method, but so powerful and very exciting. I think that's kind of I don't want to say this class is simple because obviously this is not simple. Does this look simple to you? Of course not. But like, it looks terrible, but like it boils down to something pretty straightforward and is extremely powerful. And that's very exciting to me. So we'll get more practice. It's challenging for sure. But when you boil these concepts down, it's actually not as much of a headache as it might first appear. So I'm excited to talk about that with you. Hope you're excited for what we've got going on in this class. Please ask me if you have questions, okay? So talk to me before or after class, send me emails, make notes as you're going down through these videos of things that don't make sense for us to talk about later. Put time, like make sure like record timestamps so you can go back later, or timestamps so you can ask me a question is very helpful as well. So best of luck. Hope you're as excited as I am, and have a good rest of your day.